My second video in my module on complex numbers, in which we take the time to define what we mean when we say a complex number. So we'll go ahead and start by excuse me, talking about what a complex number is and how it is written. So first things first, a complex number is any number that can be written in this following form right here, okay? Where we say a and b, these a and b parts, they are real numbers. And we say I squared is equal to -1. That is, like I is our imaginary unit, is equal to the square root of -1. So I squared is equal to -1. These two things are fact going into this, okay? But we refer to this as being the standard form of a complex number, okay? This a plus bi form. It's really important that we know what standard form means, because we're going to be writing all sorts of numbers, complex numbers in standard form, okay? So as far as what the anatomy of a complex number looks like, we say this entire thing is a complex number. But we call this a part out front, okay? The a part is called the real part of the complex number. So we say the real part of the complex number. And where the b part, okay, so now this is really important. People tend to confuse this. We say the bi part or the b part. We actually refer to the number b, just the number b, not the I, as the imaginary part. So I know that the b is resting right next to the imaginary unit I, but we refer to just the number b as the imaginary part of this number. But all complex numbers really are a simple sum of a real number with an imaginary number. So a real number plus a non-real number. And as a matter of fact, these are not like terms. They never go together. But that's what a complex number is, okay? We'll take a look at a few solid examples of what they are next, but I do want to make a few mentions here, or mention a few things. It is very, very true that if the a value here is 0, so like we said, if a equals 0 and b does not equal 0, then what you end up with is a number that looks like this. We say a plus bi, where a is equal to 0, so you get 0 plus bi, which is just bi. And so this number gets a name. This is called a purely imaginary number. So essentially, we look at numbers that have a real part of 0. If the real part is 0 and it's just the imaginary part, then we call it purely imaginary. Whereas if we were to say, well, in this instance, what if a is not equal to 0? The a part of our number, the real part, is not 0, but the imaginary part is actually 0. Then we look at an instance where we have our number in our complex number in standard form, a plus bi form, where the real part's first and the imaginary second. We'd say, well, then a exists, but we're saying plus 0 i's, which in essence causes your I to drop out. So we say it's just equal to a. Okay, and if it's just equal to a, we refer to this as a purely real number. You just say a real number. Okay, so the important thing to recognize here is that a real number really is an imaginary number. It just has 0 for an imaginary part, and an imaginary number, a purely imaginary number, is really a complex number. It just has 0 for a real part. Okay, so the question then becomes like, well, what numbers are not complex numbers? And every number is actually a complex number. It just may be that when you've looked at real numbers and imaginary numbers that are been purely real or purely imaginary, it's just that had a 0 for a real or an imaginary part. Okay, so in terms of examples of complex numbers, okay, we say example A up here, we say the number 3 plus 2i. So I'll write down here to give a little more writing space for it, but 3 plus 2i is a complex number in standard form. We can see this because we've written the real part first and the imaginary part second. So we say in this instance, we say A is 3. B, or the imaginary part, is just the 2. It's not the 2 and the I, but it's just the 2. Okay, so we would say this is a complex number in standard form. Where on example B here, you notice that I've got the number -7i. We say -7i is still a complex number. It's not written in standard form at the moment. Remember, a plus bi form is the standard form of this. So to write this in standard form, we would actually write our real part, which doesn't exist. So we'd say 0. We'd say a is 0. And b in this case is -7. So in standard form, this number would instead look like this: 0 plus, you gotta have a plus there, -7i. This is the standard form of this complex number. And then last but not least, by the way, so we say this is a purely imaginary number because it did not have a real part. So purely imaginary number. The next and last number I want to look at here is like 4. 4 is actually a complex number. So we say 4. The reason why it's complex is because we can write this as 4 plus 0i. And so this is our complex number in standard form. It just so happens that our imaginary part is 0. So we say 4, b is 0. And we would call this a purely real number, purely real, because its imaginary part was 0. So going ahead and looking at one really quick important relationship before we move on to equality of complex numbers is this. I make a note here. We say it's important to note that the real numbers are a subset of the complex numbers, as are the imaginary numbers. So what I want to do is I want to sketch this relationship here. So we say right here, this box, we're going to say represents the set of all complex numbers that ever are and ever were. So we say complex numbers. And what we need to say is basically this. We say we can split it in half. I don't want to say it's necessarily half. I'm just saying we split it in half for our sake. We say here are the real numbers, here are the imaginary numbers. When you discuss a complex number, what you're really saying is it's a combination of a real and imaginary. We know a few things about this. First of all, these two sets are mutually exclusive. That means they don't overlap. It's not like a Venn diagram. There are no real numbers that are also imaginary, no imaginary numbers that are also real. So we split it evenly. And we say that this real part is like our A part, and the imaginary part is our B part. But every complex number, whether it's just a real or just an imaginary or a combination of the two, but every number is a complex number. So what I want to do before we end this video is this, talk about the equality of complex numbers. That is, if I were to say there are two numbers, a plus bi, and I happen to, say that, hey, guess what, this number equals this number. The thing I want to point out is this can only ever be true. A plus bi is equal to c plus di if and only if they're real parts. So that would be, this real part would have to be equal to this real part. I mean, if they're the same person, then these two parts would have to be equal. So we could conclude that A is the same thing as C. And we'd say, well, if they're equal also, their imaginary parts must also be equal. So B would be equal to D. Okay, so these are the two things we want to admit before moving forward. Well, let's take a look at the two examples that I've written here. We actually should be able to solve for x and y if this is true. So we say we have a complex number here. It looks kind of funky, but what I want you to recognize, this is a complex number in standard form. We say A plus bi, where in this case we say A is actually equal to this entire real part, 3x minus 9. That's what A is. We say our imaginary part, B, is 4. As far as the right side of this goes, we say here's our real part, here's our imaginary part. Over here we say this is like our C and our D up top, but we'd say C is 6, and our imaginary part here is 3y minus 2. But what we're trying to admit is this. These two complex numbers right here and right here can only be equal if, say, this negative 3x plus 9 and this 6, they are equal. So off on the side we can say, well, negative 3x plus 9 is the same thing as 6. Let's go solve for x. So we just do this by doing algebra. We'll subtract 9 from both sides. We get negative 3x is equal to 6 minus 9 is negative 3. And dividing both sides here by negative 3, we end up with this. X must be equal to 1. We'll put this in our back pockets. Furthermore, we say these two numbers can only be equal if their imaginary parts were also equal. So b, which is our 4 here, would have to be the same thing as this 3y minus 2 thing. So we can equate these two things off on the side. So we'd say 4 is equal to 3y minus 2. Solving this for y, we'd say, well, adding 2 to both sides would help us isolate the 3y. We get 6, and then divide both sides by 3. And so we get y is equal to 2. So we were able to solve for x and y in a very trigonometric sense, which is, just kind of a trig class that I'm doing this for. But we say find all x and y, for which this is true where x is a non-negative number and y is less than 2 pi. Okay, so we say that the following equation is true. What if cosine x plus I sine y is equal to sine x plus I? The interesting thing is I need us to recognize right off the bat we have a plus bi. A plus bi on the left, and then on the right we could say kind of like, let's put my b line underneath this part here. I say a plus bi. And then on the right here, we kind of have like our real part, which is c, plus our imaginary part, di. Okay, so di. We could say, well, in this case, and then a is our cosine of x here on the left, and our b, our imaginary part on the left-hand side, is the sine of y. And then on the right side here, we say our c, or our real part on the right side, is sine of x. And our imaginary part on the right side, this is interesting. We say, what are we taking times I right here? It's actually a 1. We say this is 1. So what we want to do is find out where the real parts, so cosine of x and sine of x, are equal. So we say cosine of x equals the sine of x. And if we wanted to solve this, we could actually just use what we know about the unit circle. Between 0 and, actually, We say all non-negative answers here because we said x is greater than 0. We say the unit circle of radius 1, there are only two places where cosine and sine actually come out to be the same value, and that would be here. We could say we get, radical 2 over 2, radical 2 over 2 on the unit circle. So we'd say at a pi force radian angle would be one place, and then we'd say also down here at this has a reference angle of 45 degrees, so we say this is negative radical 2 over 2. Also negative radical 2 over 2. But dividing those out, you get them equal as well. We say our cosine is the same thing as our sine in both of these instances. So we could say pi force and 5 pi force. So we say x equals pi force and 5 pi force. And on each of these, I suppose we could put plus any full rotation plus 2 pi k, to be technical about it. This is what I care about. You can find those two right there. And also, this next one here, we say, well, set the imaginary parts equal to one another. Where does sine y equal 1? And again, we could just use the unit circle here. Sine y equals 1. We could take the arc sine of the sine inverse of both sides. So we say, well, y equals the angle. And when you take the sine of it, you get 1. Well, there's only one place on the unit circle, one angle that gives me a sine value of 1. And that's up here at a pi halves. So we say y equals pi halves. Okie doke. Cool.